Hello guys! I am Can Joseph Aronquillo.
Hello, my name is Bea Saira Manggarin.
I am Althea Eustaquio.
I am Jocelyn Hida.
Hello, I'm Baja Clarstel.
And we are here today to present what about the viscous and inviscid flow. Without further ado, let's get started.
What is viscosity?
Viscosity is the measure of fluid's resistance to flow. In simple terms, it's how thick or sticky a liquid is. Imagine honey compared to water. Honey is more viscous because it flows more slowly. The nature of viscosity depends on the internal friction between the fluid's molecules. High viscosity means more resistance, low viscosity means easier flow. So, to further explain this, when a fluid has high viscosity, its molecules are more tangled up and resist sliding past each other. Picture it like a crowd where people are holding hands. It's harder to move through because of the connections. On the other hand, low viscosity fluids have molecules that slide past each other more easily, like a crowd with individuals moving independently. In essence, viscosity is about how freely the molecule in a liquid can move, affecting how easy the fluid can flow.
Viscosity refers to a substance resistance to flow. In essence, how fluid it is. A substance with a low viscosity will have very little resistance to flow, meaning it flows easily and quickly, while a substance with high viscosity will strongly resist flow, meaning it flows very slowly. Let's look at some examples. Water has a low viscosity. It flows easily, spills out of a glass, splashes in a pool, and runs down your face when you cry. Other examples of low viscosity fluids include oil, milk, and blood. Honey has a high viscosity because it has a high resistance to flow. You have to squeeze the container to get it out, it globs up, and it has to be spread around with a knife. It does not easily flow. Other examples of high viscosity fluids include molasses, glue, and even peanut butter, which has such a high viscosity it acts like a solid. It's also important to note that viscosity varies with temperature. Heating up honey in the microwave decreases its viscosity.
Here are some practical application in viscous flow. In oil industry, viscous flow is crucial in oil pipelines where the flow or thick crude oil must be controlled. In medicine, blood flow in arthritis and veins in a viscous flow important for understanding cardiovascular health. In food industry, viscous flow principles are used in the productions of sauces, creams, and chocolates. In chemical engineering, mixing and pumping of viscous chemicals in manufacturing processes. In aeronautics, understanding airfoil drag due to the viscous flows helps in aircraft designs.
Hello, I'm Baja Clarstel and I will be discuss the inviscid flow. Inviscid flow can be defined as the flow of an ideal fluid which exhibits zero viscosity. This implies that there's no internal friction within the fluid, and such as shear stresses are non-existent in the flow of an inviscid fluid. It provides a simpler framework for theoretical analysis, even though no fluid is truly inviscid in reality. Some key features of inviscid flow are no energy lost due to the internal friction within the fluid. Second is the flow is reversible, meaning it can return to its original state without any loss of energy.
Viscosity is a fluid property that is closely related to its flowing behavior. When fluid flows, shear stress develops within the fluid. This shear stress at given surface is proportional to the velocity gradient exists in that plane. The constant of proportionality is called coefficient of dynamic viscosity. The viscous force developed due to the shear stress is important when we analyze fluid motion. In this video, we discuss about an assumption sometimes useful for easier mathematical description of fluid motion. An inviscid flow assumption implies that for a given flow the viscous forces can be neglected. For example, consider steady flow of air around a cylinder. We discussed about streamline patterns that are used for a better representation of such flows. Streamlines are imaginary curves where flow velocity vectors will be tangent to it. In this description, We imagine that the fluid particles slide along these curves. For analyzing motion of a fluid particle, the forces due to pressure, gravity and shear stress are normally considered. For inviscid flow assumption, the viscous forces are neglected. This assumption is valid when the relative magnitudes of pressure and gravity forces are at least an order of magnitude higher than the viscous forces. In practice there is no inviscid fluid, but an inviscid assumption will be useful for easier mathematical description of fluid motion.
So now, let us talk about the practical applications. In aerospace, inviscid flow concepts are used in aerodynamics for the design of aircraft wings and bodies, while in hydrodynamics, understanding inviscid flow helps design efficient ship hulls. While in weather prediction, simplified models of inviscid flow assist in weather prediction. Moreover, in sports equipment, designing streamlined shapes for sports equipment like racing and car bicycles. Lastly, in environmental modeling, it is used in simulating large-scale ocean and atmospheric circulation patterns.
In the fluid realm where current plays, Viscous whispers in dance this way. A molasses tide slow and thick, contours bending a viscous peak.
Inviscid spirits, swift and free, whispers of air, a melody, smooth like silk with no restraint, a dance of atoms, a boundless starring.
Viscous rivers, a languid flow, dragging tails of molecules in a tow. Frictions grip, a subtle hold, a ballet in motion, a story unfolds.
Inviscid whisper, a fluid ballet, effortless motion, unbridled display, no viscous bands to hinder or delay. In the dance of fluid, they gracefully play.
In the fluid realm, where currents play, viscous whispers slow in a gentle sway. Molecules dance a sticky ballet, resistant lingers as they find their way.
Inviscid spirits, a grateful flight, silk and steam, untethered and light, not changing forces, the various might. They glide and swirl in pure delight.